All right, so everybody's writing down the essential questions. Okay, we're going to kind of review a little bit where we were before break. And today's is pretty easy. Okay, so before the break, we were trying to solve this problem, right? I gave you that object. I said, how do we find the area of it? So what we did was, we filled it in with some rectangles, filled them in going from the left, filled them in going from the right. We got close to the area, but we still had all these gaps. So we need to figure out how to fill the gaps. We said, well, maybe if we had more rectangles, that would fill it in better. But it would be great if we had like an infinite amount of rectangles that we could fill in there, okay? So you know how when we integrate, we have the dx in the problem, okay? That really stands for the change in the x, okay? So the dx, really the length, or the width, this little in here, of an infinitely small rectangle. And we take all of those little rectangles that are infinitely small and we add those up, okay? Remember back in last year we used that for adding, right? That means the word sum, okay? Well, this year we convert this into an integral symbol. It means we're going to add up all the little rectangles, okay? So we're going to go through a whole bunch of slides where it gives us all the mathematical versions of that. I know you've got to fill in a little bit here and there. Okay. Is there anything to fill in on that one? I don't remember. Yeah. Okay. So fill in what you need to fill in. And I will talk about it again here. A lot of it's notation, and as long as you understand the basic concept, you don't have to memorize all the notation. Do not have sit here. So we talked about Riemann sums, we talked about LRAMs, we talked about RMs, midpoints, trapezoids, all that stuff before break. That was our whole focus that week before break. So what's really happening is they usually give us a beginning value and an ending value, and when we add them up, we take care of. And really what we're doing with a Riemann sum, and there's our little sum symbol, okay, is we're taking the sum of all the rectangles. So this is really this is the base of the rectangle, and that's the function is the height of the rectangle. So that's what that notation is meaning. We're adding up the product of all the rectangles, okay? So then we can take that and we can convert it into an integral. Do you have to fill in there? Yeah. Yeah, fill in really quick. So what an integral really is it's the limit as our change approaches zero, okay, of the sum of all the rectangles. Well, the good news is the way that we can, there's a special way we can convert and write that limit. We basically convert that sum into an integral symbol. And we have what we call a definite integral. You guys have worked with what we call indefinite integrals, because remember they didn't have little numbers or letters there before, right? Now we're going to add a number or letter there. So we're going to go from a lower limit, I call an upper limit, Okay, or sometimes I'll say bound, lower bound, and upper bound. They're kind of interchangeable. And then we integrate the function. And that integral on on those two limits, that gets us the all the little rectangles added up. So it's a shortcut for actually doing a Riemann sum by hand. I'm not saying that you don't ever have to do a Riemann sum by hand again. You do, because you have to do it on the AP test. Okay, but integral is basically a Riemann sum. Okay. All right. So in order to integrate, our function has to be a continuous function. If we have a break somehow, so we had a parabola and a line, we can't, if there's a gap in there, we can't integrate the function through the whole thing. We'd have to integrate pieces of it. Okay. If it's like that, we have to also integrate in pieces, right? We'd have to integrate the parabola up to that x value and integrate the line for the rest of it. Okay. Cleaner way of writing the area? I'm not sure. Is there? Yeah, so in order to find the area of a region, instead of doing rectangles, we can now use okay, so you like this first part. Okay, it looks awful, but it's not. It says, set up a definite integral that yields the area of a region. Do not evaluate it. So all we have to do is set it up. Believe it or not, AP Calculus is probably one of the few tests where you don't have to finish solving the problem to get full points. Okay, because they will actually have some that say, do not evaluate it, just set it up. Either it's something really simple to evaluate and they know you could do it, right? Or it's something super complicated and setting it up is most of the battle. Okay, so they might not have you evaluate it. All right, so first thing is first, there's our function. We know we've got to integrate it. We're going to throw that into the integral symbol. Technically, you're supposed to put parentheses around it because that little change in x technically should be distributed over both terms of the function. Okay? If you didn't put the parentheses, I probably wouldn't mark it wrong, but I would definitely write your parentheses in there for you, letting you them. Okay. Now we have to decide where it's going to and from. So what's the smallest x value here? 0, good. What's the smallest y value? Oh, sorry, bigger x value. 2. And it always should be the smaller number on the bottom and the bigger number on the top. In a minute, we're going to see what happens if we don't have that. Okay, and that's it.
How do you know it's always that?
What's wrong, Or Dante?
Okay.
You okay?
Mm-hmm.
All right. All right, we all good with that one? Pretty easy so far, right? Maybe I'll make it harder in a minute. All right. So on this one, we're going to set up our definite integral. We know that this thing's going to go on the inside of it, right? Because that's our function. So no matter what they give us, we write it on the inside. What do we have to put after it? dx. We could put parentheses around it, but it's a fraction. It kind of implies the parentheses. All right, what's my starting x value this time? Okay, what's my ending x value? Good. Done. Right? Set up. We don't have to integrate it. We just have to set it up.
So will those numbers be given to us like the 2?
They should be, yes. Or it's very obvious from the graph, okay, what the area is. They might give you a shaded region. It could be some, eventually it's going to come down to, we've got two functions that cross. Do you see the region that it created? So the x values are very obvious, okay? So, and sometimes, notice we did it with dx, right? Sometimes they switch it and they go dy, so we would have to use the y values, okay? That doesn't happen today, but it will eventually, okay? All right, I think you have to fill in blanks there, right? Mm-hmm. Okay, so fill in those two. It's these two back here, right? This one and this one. So today is all about learning little tiny properties. Okay, we aren't doing a whole lot of integrating today. We save that for the next 2 days, but we're learning a bunch of little properties and getting used to those. Okay, so this first property is saying that if my upper and my lower limit are the exact same number, what does it integrate to? 0. Think about that. If I took A and I subtracted A, what would I get? 0. So it makes sense, right? Okay, this one is saying, because remember, A is your small number, okay, and B is your bigger number, all right? If my bigger number starts on the bottom and my smaller number starts on the top, and sometimes they'll do that, we'll put 0 to a negative, that's when you usually see it. What we do to compensate for that, because we know the smaller number has to go on the bottom, is we swap their spots, and what do we get to throw out front? A negative sign. The 0 one doesn't come up as often, but this one comes up all the time. So you have to know the lower number goes on the bottom. To flip it, you flip it, and you add a negative out front, and that gets you where you can integrate it. Okay? All right. The additive property. Write it down. I'm guessing it's not there. All right, so what this one is saying is that there might be somewhere in the middle of the function where we need to break it up. So, as I was saying earlier, if we've got a parabola and a line, and they want me to integrate from A to B, these are not the same function. So I would integrate this piece here from A to C, and then integrate this one from C to B, because I can't integrate them together, okay? All right. You got to fill those ones in, or are they there? Fill in. Okay, so I think it's probably this back two, huh? All right, so what this is saying is if I have a number, so K or C both kind of stand for constant, so if I have a number or coefficient here in front, I'm allowed to take that out of the function and throw it in the front, okay? And sometimes it helps to just get that out of the way. Sometimes we leave it in, it doesn't matter. But a lot of times you'll see, especially in today's stuff, they'll put it out front, okay? This is saying if we are adding and subtracting two functions together, we can take them apart and add and integrate them individually. Sometimes I do, sometimes I don't. It depends on how complicated the function is. If it's x squared plus x plus 1, I don't take them apart, okay? Something worse than that, I probably would. All right, so the way that we're going to integrate today, integration we know is just area. So sometimes they will just give us a picture. Your book is asking you to sketch the picture, okay? But a lot of times on AP, they'll give us something that looks like this and this and this and that, and we'll have to find the area of each one of the objects, okay? So let's talk about area, or what this object looks like. So we're supposed to use a geometry formula to integrate it, okay? So if I rewrote that, it would just be this, wouldn't it? So what's that a picture of? Okay, it's got a slope. What's it a picture of? A line, right? The shape we would say would be a line. What's its y-intercept? 0. Okay, and then what is the slope? Up 1 over 2. How many times, where do I stop? When my x value equals 4. Did my x value equal 4 yet? Okay, so I got to do this again, right? So if I were to look at the shape I just created, what shape is it? Triangle. We already know how to do area of a triangle, don't we? 1/2 base times the height. What's the base? 4. Good. What's the height? 2. Okay. What happens? What can I cancel? 2's gone. What's my area? And I know, I think Zach asked before break, if we have to label units squared. If they don't give us in inches, a meters, a yards, you don't have to label it, okay? We don't usually put that generic like we did in geometry. You put a generic unit squared or whatever on it. You don't have to do that in calculus. The only exception would be if it somehow said indicate units of measure and they didn't give you one, but I've never seen that happen, okay? All right, let's look at the next one. The next one's a little bit rougher, okay? Back in geometry, okay, because I know we didn't do it in advanced algebra 2, trig, or math analysis, okay? That was the one thing we missed, was conic sections, okay? You talked about parabolas and circles in terms of conic sections. You did that in geometry. That was the equation of a circle. If you look up here on my sign that says conic sections, see the one that says circle? All that's missing is our HK, right? And remember, HK is a center, or, you know, that's how you add to the X and the Y to shift it all over the place. Well, we aren't shifting it anywhere. It's centered at 0, 0, okay? So if you take and you look at this, I'm going to get rid of the R and I'm going to put the 4 in there, okay? So I'm going to try to recreate this equation so you believe me as to what it is, because we all could agree that's the equation of circle. We've seen that before. I'm going to get Y by itself. How do I move that X? Subtract it. So 4 minus X squared. And then how do I get rid of the squared? Square root. Now, typically when we take a square root, don't we do a plus or a minus? Yeah, but did they do a plus or a minus? Did this one up here do a plus minus? Is there a plus minus in front of it? No, so in order to make it a function, because a circle on a graph isn't a function, is it? So we can't integrate it unless it's a function. So in order to make it a function, they're only using the positive half of the circle. So that's what we're going to graph, is we're going to graph the positive half of the circle, okay? So where did we say that that circle was centered? 0, 0. And then what I do is I count out my radius. Remember, this is r squared, so how long is the radius? 2. So I'm going to count out 2 in each direction. And what do you know? We've got our nice little half circle. And aren't we going from, look at your limits. Did we get the -2 to +2 on the limits? All right. So the geometry formula we would use would be the area of a circle. So what's the area of a circle formula? Pi what? R squared. Now, but do we have a whole circle there?
No.
What do we have? Half. So we have to divide by 2. Okay, what's the length of the radius? 2. Or 2 squared, which is 4. I'm good with that. Either one you want to do. Okay, 2 is going to cancel. You may leave your answer in terms of pi. We rarely multiply out the pi. Okay, so 2 pi. So what you kind of have to get used to is on one of these is the fact that when you see something like this, you need to translate it in your brain that that's really a circle. Okay? If you have to put that graph in the calculator and you're going to look at the graph and go, oh yeah, it's half the circle. Okay? Let's keep going. So now they're basically going to try to apply these properties we wrote down a few minutes ago. Okay? So what I'm saying here is if when I go from 2 to 4 of x cubed dx, my answer is 60. When I integrate 2 to 4 of x dx, my answer that I get to replace is 6. And when I go 2 to 4 of dx, my answer that I'm going to replace with is 2. Okay? So I'm going to use the properties, and once I get down to one of these, I can substitute those numbers in. So I'm not really integrating, I'm doing the properties. So one of the properties was when I have a coefficient, where am I allowed to put it? In front. So I've got 3 times, from 2 to 4, the integral of 2 to 4 of x dx. Okay, now we're going to use substitution. So when I go from 2 to 4 of x dx, what's my answer? 6. What's 3 times 6? 18. Multiplying, not adding, right? Okay. It's all right. It's the first lesson back from break, right? Maybe we forgot to multiply, how to multiply over the break. All right. I had to relearn multiplication after my senior in college because I only worked with zeros and ones that year. So, all right, we good with 5? All right, looking at 6. I got to try to get it down to these things here. So one of the other properties is if I have two functions, I can take them apart and integrate them separately. So that's what I'm going to do with this one. So from 2 to 4 of x cubed. When I do that, technically this gets distributed, so I throw the dx after both of them. Of 2 to 4 of 2 dx. This one I know I can replace. Is there one that looks exactly like this? Do I have a 2 dx anywhere? In one of these three? No. But I could take that number and put it in front, couldn't I? So let's do that. And I know I'm showing more steps than I probably would normally do. Normally, when you see this, you're going to get to the point where you automatically just throw it in the front. And I might do that in the next example or two here. Okay, so what am I allowed to replace the x cubed dx with? What number? 60, good. The 2 is going to drop down. What are we going to replace the dx with? 2. 2 times 2 is? 60 plus 4 is? 64. See, not too bad today, right? We've only got 2 left. All right, looking at example 7, okay? Same numbers again. I'm going to split it up into 3 different terms. Oh, what did I forget at the end? dx, that's important, right? Because that's the width of that rectangle. We don't have the dx, we don't have the width of our rectangle. You will notice that every so often there's a typo and the dx is missing. So you put it in, okay? All right, so I'm going to, when I see the coefficient, where can we automatically put the coefficient? In front. So I'm going to do that as we go through here. So I've got 4 from 2 to 4 of dx plus, I'm going to put the 3 in front, 3 from 2 to 4 of x dx minus from 2 to 4 of x cubed dx. So I tried to eliminate a line of work for us by putting the coefficients in front right away. Okay. All right. What can I replace the dx with? 2. So I drop the 4 down, I've got 4 times 2. Drop the 3 down, what goes in for the x dx? 6, good. And then what goes in for the x cubed dx? 60, good. All right, 4 times 2 is? 8, 3 times 6 is? 18 minus 60. 8 plus 18 minus 60 is? You all have? 34, 36? 34. All right. We got one more. I think that the same typo is on yours. Is there a typo? Does this say 2 to 4 or do you have something else? You have the 3 to 6. Okay, yeah, I didn't get it fixed in here. So 3 to 6, f of x dx equals -1. Okay, so they basically gave us 4 of these things to deal with. This is another way you can see the approach. If we're going to go from 0 to 6, all we have is 0 to 3 and 3 to 6. But if I added them up, would I go all the way from 0 to 6? Is that going to be okay? So what we would do with this first one is I would go 0 to 3, f of x dx, plus from 3 to 6, f of x dx. So what number gets substituted in for the 0 to 3? 4, okay. And then what number gets substituted in for the 3 to 6 part? -1, and 4 plus -1 is? 3, good. You have to create the interval, right? They said they wanted to go all the way from 0 to 6. We only had from 0 to 3, and then it picked up again from 3 to 6.
Oh,
Okay, it's like we had this, right? A parabola, and then it turned into a line, so I had to go from here to here, and then there to there. Okay? I just switch functions. All right, what's wrong with this picture? What number is supposed to be on the bottom? Smallest number goes on the bottom, right? Is the smallest number on the bottom? No, so how do I change it? What was the rule? You make it negative, and then we go 3 to 6, right? So now for this back part from 3 to 6, what number gets substituted in? So I've got a negative from outside the function, times a negative 1. So negative is going to be what? Positive. So this one is just 1. All right, we don't even need the function for c. What's c's answer? A number to itself when we integrate it is always 0. All right, last one here. We got to take that negative 5. Where should we technically put it? In front. So negative 5 from 3 to 6 of f of x dx. What number gets substituted in for the 3 to 6 part? Negative 1. So negative 5 times negative 1 is 5. Good job. Okay, so the assignment I'm giving you is technically going on the Monday stamp. We will fill in here later in the week, probably split something up at some point to get it all filled back in.
why is number C0?
C0, because when you go from a number to itself, it's 0, right? It's like saying 3 minus 3. Okay? Tomorrow, that'll probably make a little bit more sense.